Okay, good day everyone. Magandang umaga po sa ating mga kawerpa, mga Filipino electrical students, and to our non-Filipino students, no, who are watching right now. So, good day everyone. So, my name is Engineer Reggie Marinay. I am here to discuss the direct current circuits part 12. So, this is entitled Norton's Theorem. Okay, so let us go over with our the first slide here. So, what is Norton's Theorem? Okay, our Norton's Theorem states that any linear network of voltage sources and resistances, if viewed from any 2 points in the network, can be replaced by an equivalent resistance Rn in parallel with an equivalent current source, short circuit current. What do we mean by that? Let's go over with our whiteboard here. Okay, so we have a Norton's theorem. This is an any linear network, any two-terminal network. You see this one? We have terminals A and B where our load resistance is connected. So that may be replaced by a Norton's current in parallel with the Norton's resistance. Unlike in Thevenin's, we have the Thevenin's voltage in series with the Thevenin's resistance. In here, we have here a Norton's current in parallel with Norton's resistance. And then, looking back at the two terminals A and B, so we have here our load resistance RL, okay? And then, the current here, IL, is flowing through our RL. This is our load current. So please take note that our Norton's current is our short circuit current. This is actually the short circuit current when we remove the load resistance RL and short two terminals A and B here. No? So pag nag-short tayo dito mga kawerpa, so this will be our Norton's current, which is simply equal to the short circuit current. Okay? When our Norton's resistance is actually equal to the Thevenin's resistance we studied before. Okay? So we have the Thevenin's resistance. Now, by current divider theorem, so solving our IL, so we have here our IL. Okay? Our IL is equal to, by current divider theorem, so take a look here. So we have here our IL that is equal to the resultant current. So take a look here. These are the two common nodes since they are connected in parallel. The resultant current is our IN, then multiplied by the opposite resistance, which is our RN. So this is our RN divided by RN plus RL. Okay? So this is our load current. That is now the equation. This is just by current divider principle. Okay, I'll be solving the three problem sets that we solved before in Thevenin's theorem. But now, I will solve this using the Norton's theorem. Okay, using the Norton's theorem. Okay, so take a look here. Let's say this is the load resistance RL, and these are the terminals A and B. Okay. So for number 1 question here, okay, take a look here in our PowerPoint. Find the Norton's resistance in the circuit shown. Find the Norton's resistance. Okay. So for number 1, we are asked to find the Norton's resistance. So that is our Rn. What is our Norton's resistance? Okay. Actually, the Norton's resistance is exactly the same as the Thevenin's resistance. Okay, so how to do it? Again, so let's say this is our 4 ohm resistor, and then the two terminals of the 10 volt must be short circuited. This one, let us remove the 10 volt source, then short the two terminals, and then we have here our 6 ohm resistor here. This one, and then let's say this is our terminals A, this is our terminals B. Then we have here our Rn. Okay? So, ito yung Rn natin, mga kawerpa. Okay? Again, assuming that we have a voltage source here, assuming that we have a battery here. Our battery will deliver a current here. Okay? Let's say we have a battery, a source, that will deliver a current here. And then, you will see that the 4 ohm resistor will now be in parallel with the 6 ohm resistor. In fact, the one current will flow here and the other current will flow here, right? That will divide into two. This current, the current from the source. Okay? So the current flows through our 4 ohm and 6 ohm resistor. So therefore, okay, our ohmmeter, this will measure all the resistance path, what I mean by resistance path, these are the resistances where our current flows. So kung saan dumalo yung kuryente, yun ang susukatin ng ohmmeter natin. Okay, mga kawerpa? So, the 4 ohm now will become basically in parallel with the 6 ohm resistor here. So therefore, this is very easy. Okay? This is our Rn that will be equal to, so we just have a two resistors in parallel, product over the sum. So 4 times 6, then over 4 plus 6. Okay, so let us calculate this. So 4 times 6, then divided by 10. So that, actually, that is 2.4. 2.4 ohms. That is also our Thevenin's resistance before, no? If you attended our lecture last time, that is also our RTH. Exactly the same. So, take a look here. The answer would be letter, okay, there you are. Letter A. That is our Norton's resistance. What about find the Norton's current? Norton's current. Okay. I said that the Norton's current, looking here, is the short circuit current. If we remove our 3.6 ohm, the load resistance here, okay, for number 2, I will remove the 3.6 ohm. So we'll be having this equivalent circuit, guys. Okay. So we have a voltage source. Our voltage source, 10 volts. We have 4. We have 6. Okay. So this is our terminals A and terminals B. So let us short these two terminals. See? I remove the 3.6 ohms, and then what will be the short circuit current here? Remember that the short circuit current is equal to the Norton's current. See? What will happen to this circuit? What will happen to this circuit? Take a look, guys. If we are going to short this one, okay, what will happen? This is a voltage source. The current will flow here from the voltage source, 10 volt source, and then there is a node here. It seems that there is a node here, but take a look. This is a short-circuited. If you short-circuit the 6 ohm, all current will just flow here. It's just like removing our 6 ohm resistor. Okay? To our non-Filipino friends, so please listen. So I have to apologize because I have a I'm not that fluent in speaking English. Okay? So I don't have an English tongue. I have a Filipino tongue. Okay? So okay. So please bear with us. So we are trying our best for you to understand the lecture. So because in the near future or later, actually, we are going to upload this video in my YouTube channel. In my YouTube channel. Okay? So please bear with us. Okay? We will try our best for you to understand this lecture. So, okay? So please bear with us. From time to time, I'll be speaking a little of our language in Filipino so that our Filipino student will also understand this lecture. Actually, this series of lecture is 2-in-1 in approach. If we have a pure Filipino student and a pure English tongue fellow men, whether you are Americans, Europeans, Africans, no? Kahit ano pa lahi mo, basta't nag-i-English ka, no? Definitely you will understand this lecture if you speak in English. No? This is not a Taglish, no. Alam natin sa Pilipinas yung Taglish eh. In the Philippines, if we mean Taglish, it is the direct combination of English and Filipino language. It's not, I'm not using that medium here. No. No. It's definitely not. What I'm doing is, I will speak first in English, and then I will convert. When I finish my complete ideas or statement, I am converting it in Tagalog, you know, in our language. Okay? So, nakuha ba mga kawerpa? Thumbs up naman dyan. Yun na, inspirasyon lang. Para ganahan lang tayo magturo. Ayun, di ba? Sabi ko, wag lang kayo sumagot. Pwede naman mag-thumbs up. Pag mo nang pakita sila, okay na yun. Nagre-recording nga pala tayo. Okay. Okay, sige, no? Hirap mag-adjust, no? Okay, ha? Okay, to our friends who are watching right now, we are also live in our Facebook, right? Facebook live stream, okay? So, good day everyone. I am discussing the Norton's Theorem. Okay, now, how to get the short circuit current here. The short circuit current is the current that will flow to the two terminals where your load resistors are connected. Your load resistor, I mean. Okay, let's go back here to our late viewers. Let's go back here. We have, take a look here. We have a our RL. I will remove RL. Then what will be left is the terminals A and B. Then I am going to short this. This is now the short circuiting conductor. This is the short circuiting conductor. Now, if I have a 10 volt source here, the current will flow here. The current will flow here, okay? Since this is the 6 ohm is already short circuited. That is short circuited. All the current here will now just flow here. Remember that. All the current will just flow here because you already short-circuited the 6 ohm. Practically speaking, in practice, they call this as the bypass conductor. Bypass conductor. Okay? Bypass conductor. I remember if there is a what we call a service head in the building. So there is a drip loop here, the service entrance conductor, and then this is now the service drop from the utility company, the service drop conductor. Okay, our utility here, just to make sure of the well banded connection, they put a bypass conductor here. I saw an installation like this. See, this is a bypass conductor. Just to make sure of the continuity of this connection. Okay? Because the problem of this connection is they become, as time goes by, the connection, yung connection nga. Okay. The connection becomes maluwag. Ano yan? Becomes loose. The connection becomes loose. Okay? To prevent this, because this is a service drop conductor from the pole and this is the service entrance conductor, we have a bypass conductor here. The utility company would connect, they will connect here a bypass conductor. So, the current now will flow here. Okay? Just to make sure that there is a continuity of service. Just like here. This is a bypass conductor. It's just like saying removing the 6 ohm resistor. So take a look here. If this is a short circuit current, our equivalent circuit now will just be like this. Okay? This is the 10 volts. This is the 4 ohms. Okay, I will remove totally the 6 ohm resistor. This is A and B. Then take a look, guys, here. This is the short circuit conductor. And there is a Nortons current. See? The Nortons current, what is the equivalent of the Nortons current? Take a look here. It's just simply that this Nortons current is just flowing around to this loop. Right? So therefore, our Nortons current will just be equal to what, guys? Okay? It's just a simple Ohm's law, right? So we have a 10 volts divided by 4. 10 volts divided by 4. So how much is this? Okay? So 10 divided by 4. So we have here 2.5 ampere. So it's simple as 2.5 ampere. That is our final answer. Okay, and the answer would be letter C. Okay? Letter C. Now, let's find the load current. Okay. Since we already have our Norton's resistance and Norton's current, we can now easily have the Norton's equivalent circuit. No? This is what we call the Norton's equivalent circuit. No? It's not the National Electrical Code, no. So it's Norton's equivalent circuit. Okay? So we have here, for number 3, guys, let us draw first the Norton's equivalent circuit. What is the Norton's equivalent circuit? So I will draw the circuit here. So we have here our short circuit current or Norton's current. Okay, then this is our, see, the Norton's current, then the RN, Norton's resistance, then our RL, then we have here our IL flowing. Let us have now the values. What is our IN? That is 2.5 amperes. What is our RN? Our RN is 2.4 ohms. 2.4 ohms. 2.4 ohms. Okay? 2.4 ohms. Okay? That one. Okay. So, Norton's current, 2.5 amperes. Norton's resistance, we have 2.4 ohm. Let us solve now our load current. Okay, again, what will be our load current? By current divider principle, what is the formula, guys? What is the formula? Again, the load current would be, the resultant current is our Norton's current multiplied by the opposite resistance of IL, since we are getting the value of IL, so that is our RN, all over RN plus RL. Okay, there you are. Then I will just substitute. I'll just go here. Okay, so this is our IL, that is, what is Norton's current? We have 2.5 amperes. Then multiplied by, what is our RN? That is 2.4 all over 2.4 RN plus RL. What is our RL? 3.6 ohms. Okay. What will be our load current? Okay, so 2.5 times 2.4, then divided by 2.4 plus 3.6. Okay. The answer is simply 1 ampere. 1 ampere. This is our load current, guys. This one. Okay? And the answer would be letter D. Okay? Letter B. Then, next question for number 4. So, this is very easy here. I'll just put it here. Find the load voltage. So, load voltage simply equal to the current at the load, of course, simply by Ohm's law, 1 times the load resistance. What is our load resistance? 3.6. 3.6. Okay? So, we have here our BL as 3.6 volts. Okay? That will be our answer. 3.6 here. And that would be letter D. Okay? So that will be letter D. Okay, I just want to teach here. I will also teach here the Thevenin's, how to get the Thevenin's voltage here. The Thevenin's voltage. Given we have the Nortons current, we have the Nortons resistance. What is the Thevenin's voltage? Okay, so I just put it in here. The Thevenin's voltage simply equal to Ohm's law. Ohm's law. What is the Ohm's law? V is equal to I times R. So simply, this is our IN multiplied by Rn. So our VTH simply equal to IN. What is our IN? That is 2.5 ampere. Then times our Rn, 2.4. We just have to multiply the current to the resistance. The Norton's current and Norton's resistance. See? What is the Thevenin's voltage here? Okay, 2.5 times 2.4. That is simply 6 volts. Huh? Well, you can take a look at our answer last time when we discussed the Thevenin's theorem. Okay? This coming Friday, I will discuss the source transformation. It is here where we will discuss simultaneously the Norton's and the Thevenin's theorem. We will apply them, no, in solving a circuit. Okay? See? Then let us go with the next problem. Okay, so we have for problem number 5. So I have to draw first our circuit. This is for problems 5 to 8. Okay, so take a look here at our figure. That is for problems 5 to 8. So take a look here, guys. So in here, we have a 3-loop circuit. So we have the loop 1, loop 2, and loop 3. So we have a 3-loop circuit. Okay, so let us have first find the Norton's resistance. Okay, for number 5 here, find the Norton's resistance in the circuit shown. So I already draw the circuit. What is the Norton's resistance? Norton's resistance. Here. What will be our Norton's resistance here? So first, so we are going to remove our RL and short the 120 volt source. Okay? Okay, so we have here our 20 ohms. Then, let's say we have here our point A. Then our point B. Then the two terminals are short-circuited here. Then we have a 10 ohms here. This is our 10 ohms. Then we have another 20 ohm resistor. Then we are to connect an ohm meter here. That is our RN. It is exactly the same procedure. It is exactly the same procedure when calculating our Thevenin's resistance. Parehas na parehas lang yon. So, always remember that in getting the resistance, you are thinking that there is a voltage source here. Then that voltage source, it will deliver a total current here. Then there is a node, one current will flow here, and this is a node, one current will flow here. Then take a look again. There is a bypass conductor here. So if that is a bypass conductor, you will see here that this current will bypass the 10 ohm resistor here. It will just flow here. Because basically this has the lowest resistance. Theoretically, it is a zero resistance or very, very low resistance. So against the 10 ohm resistor, of course, by Ohm's law, so V over R, if we have a very low resistance, there you will have a very high current. And this current will flow to a very low resistance. Always remember that. So the current will just flow here. So it's just simply, okay, I will draw the equivalent circuit. This 20 ohms, okay, it's just as simple as removing, okay, I will not draw anymore the equivalent circuit. Take a look here. See, I already removed the 10 ohm resistance. Now, this is now useless. That is idle. Already idle. So, we may see here that this 20 ohms will be in parallel with this another 20 ohms here. They will just be in parallel. So, it's just simply, we have a two resistors, two 20 ohm resistor in parallel. 20, 20. Then, this is our Rn. So, therefore, our Rn now, guys, is this. Identical resistors in parallel. Branch resistance, 20. Number of branches, how many? 1, 2 branches. There are 2 branches. So, 1, 2 branches. So, put here 2. So, therefore, the answer is 10 ohms. And that would be letter, let's go over here. The 10 ohm resistor is letter C. Okay? Letter C. Then let's go now with problem number 6. Okay, that is problem number 5. Then let's go with problem number 6. The question is find the Norton's current. Let's go over here. Find the Norton's current or the short circuit current. Take a look here, guys. I will redraw the circuit. I will remove RL, then short terminals A and B. So we have here our 20 ohms. Okay, that one. Then we have here our 120 volts. Here. Then this is our 10 ohms. And then this is our 20 ohms. This is our 20 ohms. Then we have here our 20 ohms. So, our problem, no? I will short circuit the two terminals A and B. I remove the 30 ohm RL. And then, the terminals A and B where your RL is connected. So, A and B, that must be short-circuited. So, the question is the Norton's current. This is the Norton's current or the short-circuit current. There you are. Again, please take a look here, guys. We have a 120 volt source. This will deliver a current here. That will be your total current. Total current. Okay? One current will flow here, and the other current will flow here. Okay? Then, it seems that there is a node here. But actually, there's no node. Why, sir? Because this conductor is a short-circuiting conductor or a bypass conductor. So, this current will just flow directly here. Okay? It will not flow through our 20 ohm resistor here. It's just like removing this 20 ohm resistor because this is a bypass conductor. Okay? All now the current here, if we mean bypass conductor, it is a parallel short-circuiting conductor with respect to your 20 ohm resistor. Since they are in parallel, this conductor is in parallel with the 20 ohm resistor. So therefore now, all the current will just go to the bypass conductor or the short-circuiting conductor. Okay? So what about? Okay, I will draw now the equivalent circuit here. Okay, this will be the equivalent circuit. Okay, so this is 20. Okay, then we have here 120 volts. And then, so we have here, remember I have a short-circuiting conductor here. Okay, this is the 20 ohm resistor, and this is our 10 ohm resistor. No? That is our 10 ohm resistor. Okay? So it's just like removing the 20 ohm resistor here. So all currents now will flow here. It will just flow here and here. Okay? But we have this current. That is our I total. Let us get first our I total. By the way, we have to get first our R total here. What is our R total? Always remember in getting the R total, this is the R total. In getting the R total, we will replace the voltage source by an ohm meter. What will be the measured value of this ohm meter? Remember, one current will flow here and the other current will flow here. It's just like saying that the 20 ohm resistor, take a look here, that will just be in parallel with the 10 ohm resistor. Right? This 20 ohm resistor, magiging parallel na lang siya sa 10 ohm resistor. Okay? So, there will be two resistance in parallel. That will be the product over the sum. So, we have here 20 times 10 over 20 plus 10. Okay? So, we have here our R total. Okay? R total. So, that is 200. That is actually 200. 20 times 10, 200, then over 30. I will not use my calculator. Okay. So, the 0 will cancel here. So, we'll be having here 20 over 3 ohms. So, that is 20 over 3. Okay, using our Ohm's law to solve for the total current. So, we have here 120 volts divided by 20 over 3. Okay? That will be our okay, it's just like saying 120 times 3 then divided by 20. So the answer would be 18 amperes. That will be 18 amperes. Now, we are to calculate the current IN. This is actually the current IN. Take a look again here. This is current IN. That is actually the current flowing to our 20 ohm resistor here. So, this is our current IN. So, we have here our IN now by current divider theorem. Our IN is equal to the total current, which is 18, then multiplied by the opposite resistance, which is 10, over 10 plus 10 plus 20. So what will be our answer? That will become 180, then divided by 30. So that is equal to 6 amperes. That is simply equal to 6 amperes. Okay? That is our answer, and that would be letter. Okay, there you are. The answer is letter B. Okay? Then let us solve number 7. Question for number 7. Find the load current. Again, in finding the load current, we have to draw the Norton's equivalent circuit, no? The drawing natin yung Norton's equivalent circuit muna natin. Or, actually, we can go directly with our formula. Okay? Our formula for the load current. Because we already have the Norton's Current, okay? And we also have our Nortons Resistance, no? Meron na tayo, kumpleto na. Okay, I will not draw anymore the equivalent circuit. I will just go directly with our formula because we already discussed that. Okay, let's go over here. Okay, so that is number 7. Okay, for number 7, again, what is our formula for the load current? Our load current simply equal to IN multiplied by RN all over RN plus our RL. So we just have to substitute here. Substitute natin mga kawerpa. Tingin pong mabuti ha. Our IN simply equal to 6 amperes. Then multiplied by RN. What is our RN? RN is 10 ohms. All over 10 plus 30. Okay? So, our answer now will be equal to, that will become 60, then divided by 40. 40. So, the answer would be 1.5. Okay? this will be 1.5 amperes. Okay, and that would be letter C. C? Okay, the answer is letter C. C? Okay. Last number. Okay, here for number 8 for this problem set. Okay. The question is simply find the load voltage. This is very easy. It's because just apply Ohm's law, of course, that is IL times RL. So, what is our IL, guys? Okay, we already have 1.5. Okay, times 30, okay, 30, 1.5, kalahati, 30, 15, 45. Okay, 45 volts. Okay, that's the answer, guys. 45 volts, and that is letter B. Okay, so that is our answer. That is letter B. Okay, guys, so we will, that is the topic for the Norton's Theorem. That is just the first part of the Norton's Theorem, no, mga kawerpa. So, we apply the Norton's Theorem for 2 loops and then for 3 loops. And then for the next video, okay, so we'll just have a short break, no, maybe around 5 minutes, okay, to our Facebook friends. So, antabay lang po tayo, no? Siguro mag-break lang ng konti, 5 minutes break. I will solve now for part 2. I'll be solving, I will apply the Norton's Theorem in a Wheatstone bridge. Okay? Thank you.